Good day, everyone. So my name is Smit. I work for the RIPE NCC. Today I'm going to go a little bit deeper into what was already talked about yesterday by Ritesh. Autonomous System Provider Authorisation. So I'm going to quickly go through some stuff about current routing. I think most of you are aware of this because, well, most of you are network engineers. So BGP is based on trust. Anyone can configure his router to basically announce anything from any ASN. It's plain text, it's all simple, based on trust. This is nice. It has its advantages. It's working for 30, 40 years already. But yeah, the shortcomings are getting painful. One of the things that was designed to address this is obviously creating root objects in IRRs, routing databases. So you would say, okay, I've got this prefix, and it's going to be announced from this origin, this AS number. That's nice, but it's plain text. You also have autonomous system numbers, AUTNUM objects in your RIPE database or other IRRs, where you can say, okay, this is me, this is my AS, and you can describe who are your downstreams, your upstreams, your peers. But again, the problem here is it's plain text, and the IRR system has some shortcomings, basically. There are very, very many IRR databases. I think about 30, 40. Over time, there has been inconsistencies. Some of them have limited holdership checks, so someone can just come along and say, oh yeah, I'm going to advertise this prefix from this ASN, can you just add it? There's a lot of stale data as well. So basically what you're going to do is you're downloading plain text data from plain text databases from various sources, and you're going to base your security on that. It works. It has been working for a long time, but it's starting to crack a bit. Comes along Resource Public Key Infrastructure, RPKI. I think most of you know about RPKI. So it's a security framework. It's much more than what most people at the moment think of if you talk about RPKI. It's much more secure. And why? Because the resource holders are appointed or linked to the resources by the RERs. It's going to be cryptographically signed, so that you know that the information comes from the person who's authorized to make decisions. We have BGP ORDEN validation, which is doing pretty well. But you can also use RPKI for other stuff, like Autonomous System Provider Authorisation, ASPA. It enables BGP SEC, which is a protocol which is interesting, but yeah, difficult to implement at the moment. But yeah, this is the system in a nutshell. You have root CAs run by the 5 RERs. They give out certificates to their members or end users. This is cryptographically signed, and it contains all the resources of that end user or resource holder, and they can then make cryptographically signed statements about their resources. So they can create ROAS They can create ASPAs, and they can create BGP SEC certificates for their routers. And now, you can actually start using filtering using authorized and cryptographically signed information. Like I said, RPKI origin validation, it's the most popular, most well-known use. It prevents misconfiguration and hijacking. Basically, someone who's not authorized to announce a prefix can be found out. It does not prevent path spoofing. It does not prevent root leaks that have the correct origin. And that is what we're going to address with ASPA. So what's in an ASPA object? Well, there's obviously some cryptographic stuff like valid from and not before and not after, blah, blah, blah. But basically it has the customer ASN. That's the ASN of the ASN being described. And it has provider ASNs. So those are the two most important things about ASPA objects. The customer ASN saying, okay, these are my upstreams, one or more. And what you can do with the data is not as much as see if a route is plausible, but you can at least find out if a route is implausible. And if a route is implausible, you can say, okay, this looks weird. I'm not going to accept that. How does that work? When your router receives a route, it will do an analysis hop by hop, AS hop by AS hop. It will mark each hop as provider, not provider, or no attestation. So I don't know, there's no ASPA object here. And at the moment that there is a not provider popping up in the path where it shouldn't be, you can just drop the route. There are two ways of validating. There's the upstream path validation. So you should use this with your customers and your peers. Basically, it's quite strict. It's not that complicated. And it allows you to verify whether a route coming up is logical. Then for the complexer cases, like your upstreams, you can do downstream path validation. We're going to look at both. But basically what it does is it will allow the AS to travel up to the top and then looks if it matches the traffic going to your tier 1 provider. So looking at an example, we have here someone who configured his router as AS4. He's announcing it to his upstream, AS5. AS5 is propagating that to AS1. We're AS1. AS1 sees a path from 4 to 5, from 5 to 3, and from 3 to 1. There's an ASPA object made by AS4 that states that the upstream is AS2. So AS1 sees this route and starts looking. Okay, so the hop from AS4 to AS5, does that match the provider? No. That hop is not provider. Then it's an illogical route. It shouldn't be there. And it's being marked as invalid and can be dropped. Now, this is a case where someone is seemingly doing something malicious. However, it might actually just be a misconfiguration where AS5 is actually a peer of AS4 and is accidentally upstreaming for AS4. So regardless whether it's a leak or a hijack, the path is still the same. The path is 4 to 5, 5 to 3, 3 to 1. And at the first part, the first hop, 4 to 5, there's a no provider. So the route is invalid. So this is the easy, more strict validation, which is only allowing someone to go up. You use this for your peers and your customers who send information up the AS tree. When you look at your transits, information is going to flow up the tree and then down again. This is a bit trickier to find out, but basically the idea is that data should flow up once and down once, and not up, down. So that's why we call it valley-free routing, or a valley-free tree. So the first step is the same. For each AS to AS hop, you verify if it's provider, not provider, or if there's no attestation. You look at each hop until you find somewhere where it's no provider. Then you reach the top of the tree. Then you look from your perspective, and you're going up the tree to see if this route is a plausible one. And you can only say if it's plausible if up and down meet at a certain point, or if they overlap somewhere. So here you can see that it's going up from the stub network on this side up to where you don't know anymore if this is a valid route. Then you go from the other side up and check if these providers are peers, and if they are, you have one tree up, one tree down. Or as the second one shows, you go to one tier 1 transit, both are connected there, and it's a valley-free route. If we look at this example, you have AS5 that is announcing a route to AS2. AS2 specifies that AS1 is their upstream. AS1 has a specific ASPA, and they state that they have AS0 as upstream. That means that they are provider-free. They state they do not have any upstreams. So if we're going to look at the route that's being received, it's AS5 to 2, 2 to 3, 3 to 1, and 1 to 4. We're looking from the perspective of AS4. So AS5 to AS2, that's a provider. Good. Next step, AS2 to AS3. AS2 specifies that AS1 is their upstream. They don't mention AS3. So they could be a peer, but they're not an upstream. So that is not provider. We reached the not provider step. So now we're going to look from the other side, AS4 to AS1. Okay, that's our provider, that's our upstream. Then we're going to look at the next hop, 1 to 3. AS1 specifies that they have AS0. They don't have any upstreams. So these trees do not match up. They don't touch. And so we see that AS3 is considered a valley. And therefore, this route would be made invalid and dropped. Same story. AS4 is in between AS1 and AS2. Maybe he's a customer of both. And he leaks his routes. He leaks the routes from AS1 to AS2 and the other way around. AS1 and AS2 in ASPA both state that they do not have providers. So we go up AS6 to AS3, that's good. AS3 to AS1, that's good. There we hit no provider. The other way, AS7 to AS5, fine. AS5 to AS2, okay. AS2 to AS4, wait, that's not provider. There is an ASN in between two parts of our route. So again, this is a valley, and it's going to be considered invalid. So how do you create ASPAs? I'm assuming, which is a bold statement, but I'm going to do it anyway. I'm assuming that most of you are working with the RIPE NCC as your RAR. So I'm going to show some screenshots from the RPKI dashboard that we created for you. The RPKI dashboard, it used to be only ROAS. We've added some information on ASPAs. For ROAS, we can look at the routing tables and make an assumption for you on what are probable prefixes and probable ASNs and which are probable origins. For ASPAs, we cannot do this. It's too dangerous because there might be upstreams that we never see. So we kept the interface really simple. We've got customer ASN. That's the ASN that you're working on, the ASN that you're creating the ASPAs for. And you can click Create ASPA and then fill in your ASNs. Here we have an example of 2121 where we are configuring the provider ASNs, so our upstreams 3333 and AS1103. We do not make suggestions. And then basically you click apply. It's being published and the world can use your ASPA to verify if the routes that they're receiving are probable. It's very, very important to include all your possible upstreams. Backup ASNs that are going to be your upstream in case something goes wrong. Scrubbing centers, which can be put in line, because otherwise you'll make the route to your scrubbing center invalid. You do not put your peers as upstreams. They're your peers. They're not providers. Important one, non-transparent root servers. I know there are some people here from Links and LoNapp, and they might know, and you might know yourself, if their root servers are non-transparent, but if they are, you should add those. And it's very important to keep this information up to date, obviously. So if you get an additional upstream, or you're going to switch upstreams, this must be updated. You need to fix your ASPA object at the moment that you're using different upstreams. How does this work in routers? Well, to be honest, not very much at the moment. But the idea is actually quite similar to origin validation. You have the ASPA statements, which are signed, published, and they get downloaded into the repository, the RPKI repositories. You install a validator or validated cache, and that downloads all the information from all the RPKI repositories that are there. They do the cryptographic figuring out if everything is okay and correct. And then, via the RTR protocol, your router gets the information from your validator. So your router is not being bugged with any cryptographic stuff. That all happens on your validator. If you run one of the most common validators, they will probably already allow the use of ASPAs as well. It is a sharp tool, as we say, like BGP origin validation. When we just started with it, it wasn't that dangerous to make a little mistake. Now, things are different. Origin validation is out there. It's being used a lot. So if you misconfigure your origin in a ROA, chances are that you won't be able to fix it anytime quickly. Make sure that you know what you're doing. Make sure to set the correct validation type for the correct type of peer. Upstream path validation for your customers, for your peers, because they are not your transit, and downstream path validation for providers. There are not many router vendors that support ASPAs at the moment, or at least making decisions on it. I think OpenBGP does, BERT does. I've spoken to a couple of people. I know that there is a test version of iOS XR available, and I know that all the other vendors are working on an implementation as well. If you want to go ahead and start doing ASPA validation on your routers, you might want to do it in the same way as most people do and did with origin validation, logging it. Maybe using a tool like described yesterday, Raven. And warn your customers, if you have customers that are using BGP, to make sure that they have their ASPAs correct. Now, at the moment, there are not that many ASPAs, but it's growing fast. I checked, there are about 2,000 ASPA objects in the various RAR databases. But yeah, it's an early stage, but it's being picked up rather swiftly, so it's looking good. Yeah, that's basically all I wanted to address here. Any questions or comments?
Hi, yes, Greg Choules, ISC. Could you go back to slide 21, please?
Can I? It doesn't seem to work. I should go. Oh. No, sorry. Ah, there we go. Which one did you want to see?
21.
21. Come. You can do it.
Yep, that
Yeah.
one. So if AS1 and AS2 are peering, presumably at an IX or something, and for this example, that peering is just broken temporarily, but normally speaking, those two would peer with each other.
Yeah.
How does this validation work if AS1 and AS2 are actually talking to each other? So,
Well, then you would have the AS path, which would be 63125. So you would see a peer, and you would have like a mountain where you go up.
but AS1 and AS2 both have listed no upstream.
Yeah, but since they're adjacent peers,
Okay.
this is an allowed setup, and this is allowed. As long as there's nothing in between them, it's okay.
Any other questions for Ralph? Then thank you very much, Ralph.
You're welcome.